Hi students, back with the design review. We are now going to look at the summing amp problem. So I'm going to treat one of the recommended practice ideas. That is, we will be looking at a case where we want to pick the resistors to give an output amplitude of the sine wave of 0.1 volts peak to peak and an offset of minus 10 volts. And then we'll look about making a change to give a positive offset and no inversion of the input waveform. So one of the most important aspects of this problem is to remember that this is the summing junction. And the reason that's important is that the voltage is always 0. And that means that it's actually a virtual ground. And that's how the summing junction actually works. Because every current that flows through any one of the branches, that is the current that flows this way or the current that flows this way, is independent. It's like having this resistor tied to ground or this resistor tied to ground. If a current flows here to ground, it doesn't really affect whether or not a current is flowing from there to ground. The amplifier, by means of its feedback, draws any of the current that flows into this junction through this resistor to the output, and most of it actually goes inside the amplifier and then goes either to the positive supply terminal or to the negative supply terminal. So it provides an output voltage in order to allow any current that flows in here to be taken away. So you can design this quite easily. That is, all you have to do is to think about this and that in relation to each other and this in relation to each other. So we really have just two independent problems. One of them is I want an input that is 0.25 volts peak to peak to give me an output which is 0.1 volts peak to peak. You notice that the gain is actually, in this part, is actually less than 1. And that's possible. Now, the other case is I've got a voltage at this point, say, or basically a current that is being sent through from the voltage source here through this voltage divider to R2. And we want to have a voltage on the output which is minus 10. So remember your Thevenin equivalence. This thing has a Thevenin equivalent which looks like a divider of V Thevenin is equal to the 15 volts times the ratio of the lower 1K to the 2K plus 1K. That is basically 15 volts times 1/3, or 5 volts. And an R Thevenin, which is the part that many students forget about, of 2K in parallel with 1K, which gives you about 670 ohms. So you always have to remember that when you replace things by their Thevenin equivalent, which in this case is like a battery of 5 volts, it is in series with a 670 ohm resistor. And that's what's going to R2. Now usually you want to make sure that you keep track of what is known as the rule of 10. You would like R2, the input impedance of this part of the summing junction, to be about 10 times bigger than the 670 ohm or more. So I'm just going to pick a resistor for R2 which is large enough, and then I will pick R3 in order to give me the output that I want. So my goal is to not change the voltage at that point. That is, I would like to assume I have something close to 5 volts right there. That makes it easy to choose the ratio of R2 to R3, and then I can work backward to get the value for R1. So I'm just going to choose a value of 24K for R2. this is easily 10 times bigger than 670 ohms. 10 times bigger would be 6.7K, so this is comfortable. Then I just need to have the fact that if I've got 5 volts there, I want 10 volts there, or minus 10 since it's an inverting amplifier. And I would want a value for R3 to be twice R2, or 48K. Now in our usual pile of resistors, there is no such thing as a 48K, so we'll use 47. That's a standard 5% value. So I've already nailed down this is going to be 24K and this is going to be 47K. That gives me approximately 10 volts or minus 10 volts on the output for that side of the problem. Now for R1, I want to make sure that I have a gain of 0.1 divided by 0.25, which is a gain of 1 over 2.5. And that should be equal to the ratio of R3 to R1. Since R3 is already established, I solve this for R1, and that is going to be equal to 2.5 times R3, and on my calculator that comes up to 117.5K, which is, I'm going to round up to 120K, which is a common value. So that's 120K. And that's pretty much the problem for the first part. The change I would like to make is to add something to the output to move the output so it's no longer inverting. And the easiest thing to do, of course, is to put another inverting stage. And you can design this almost any way you like. You just have to have an output, connect it to another inverting amplifier, and that is some resistor in the input path, another ground, this is coming out on minus, that's plus, a feedback resistance. And if I just wanted unity gain, so for example I could put 10K here and 10K there, and then the output would give me a 0.1 volt peak to peak sine wave and an offset of plus 10 volts rather than minus on the output. And that's all there is to it.